PCS members and friends to our PCS IBS seminar. It is a pleasure to have with us today Professor Son Nguyen from École Centrale de Lyon, Institute for Nanotechnologies from France. And this time he's with us in person. And our scientific host is Zung, who will introduce our speaker.
So we're very happy to have Son Nguyen from Lyon today to give a seminar on photonic crystal. Son graduated his PhD at Pierre and Marie Curie University in France. After 3-year postdoc at CNRS Laboratory of Photonic and Nanostructure, he joins Institute of Nanotechnology in Lyon as a faculty position. And today he will give us a talk on engineering band structure and non-Hermitian states of life in a photonic crystal. Let's welcome the speaker.
So good afternoon, everybody. First of all, I want to express my pleasure to be here today in person. It's 2 years ago, just after the COVID. I already gave a seminar, but it's remote, and now I can see you here, and especially I want to thank Zoom for inviting me to Korea this time. So Zoom, we share more than 20 years of friendship. We were in the same high school together, learning physics at high school, and now we are doing research together. So I think it's a very beautiful story. So today I will present you how we propose a new way for engineering band structure and non-Hermitian states of light in photonic crystals. Let's try. Okay, it works. So photonic crystals, as you all know, are optical nanostructures in which the reflective index of the matter is modified periodically in space. So today I will mostly focus on this case that we call photonic crystal grating. The reflective index is changed along each direction, light is confined vertically, but sometimes can leak outside the structure. So these type of the crystals belong to a family named photonic crystal slabs. And you can also have the 2D version of this, or you can see that the periodic structure is 2D within the in-plane X and Y, and we have the vertical confinement. So what is the difference between solid crystals in physics and photonic crystals? So for this crystal, we solve the Schrodinger equations for electrons. And in particular, the Coulomb interaction is a periodic function, of space. And for light, we solve very similar, same but different equations, Maxwell equations. So instead of having the potential VR, the VR potential is replaced by the dielectric function, which is also a very function for light. And if you compare the two equations, you will see that they are all eigenvalue problems of particles in periodic potential. So we can apply the Bloch theorem. So the eigenmodes of the system contributes to the electronic band structure for the case of solid crystals and photonic band structure for the case of photonic crystals. So let's take a look also. So here, I think I take this picture from the Astrup and Mermin's books. We have the band structure of electrons in silicon. And this one is, I took from also a textbook, very famous textbooks for photonic crystals, moving the flow of light from MIT groups. So as you can see, so they look very similar. We have some kind of spaghetti diagram that dictates the properties of the particles, electrons, or photons in the solid. But for the photonic part, don't forget that we are working with vectorial quantities, electric field, magnetic field. So instead of having scalar wave function, we have vectorial field, so we have polarization. It's a little bit more complicated, but also it gives some new flavors for light. So we can have TE or TI modes, for example, in this case. But then also in photons, what we like sometimes is the spin degree of freedom that you have for electrons. You can replace these spin degree of freedoms by the pseudo spin given by left and right signal polarization. Other than that, also in the case of photonic crystal slab, one that I show you here, if we put photons inside, sometimes light don't want to stay in the slab, even we have the vertical confinement, and try to escape out of it. So in general, in photonics, we are always dealing with losses, and sometimes we rely losses. If you take LED, a laser, any lighting, actually we are engineering losses. And also we need the system to interact with outside solar cells. We want to have absorption. So in general, we are dealing with open system. In the case of open system, and we are solving eigenmodes, so the eigenmodes is represented by resonances that can be probed in transmission, reflectivity, or photoresistance. In general, we have this kind of shape. So the position of the place is the frequency of oscillation, the real part of energy, and the line width, there's the damping, so losses. In general, we would like to write the eigenvalues problem as a complex energy. Its real part is oscillation frequency, and the imaginary part is the damping rate. So how to situate this kind of complex energy? How we distribute this on top of the band structure? This will be the main recipe of today. So how to tailor on demand the shape of our spaghetti and also the thickness. Of course, we cannot have some kind of magic recipe. By the way, it will be very difficult to have some kind of line note like this. But I hope that after this presentation, you will discover that there are a lot of degree of freedom that we can take. Okay. So before going into details, our recipe, let's also introduce some textbook notions that is only exists for the case of photonic crystal slab. So if I show the photonic band structure for the crystal slab, there is a very important line we call light lines. It's given by the very simple equation omega equal to c times in-plane wave vector k that separate the band structure into two regions. One region is above the light line that we call the light cone, and the second region below the light line. So above the light cone, every in-plane wave vector can be associated with some emission angle or incident angle. So that means if I put emitters, for example, inside my photonic crystal and emit light, light can escape outside of the structure, correspond to an angle theta. So of course, if we are at the light line, then theta is equal to 90 degrees. That means that the emission will be very, very lazy like this. So in this case, we are exposing with losses. So the photonic modes here is in interaction with the radiative continuum of plane wave outside. So they are lossy modes, or here we call this also radiative modes, because we neglect all other type of losses like non-radiative losses coming from absorption, absorber, for example. And these kind of modes have application in display, laser lighting, solar cell detectors. Then below the light line, we have the second regions. Now, this in-plane wave vector cannot be associated with any angle. In other words, this K in-plane corresponds to an imaginary part of the KZ. So light, if I put emitter inside, totally reflected. So we are talking about guided mode. So there are no losses. So these kind of modes are perfect for integrated photonics. So the light line divides the band structure into thick spaghetti radiative modes and super thin spaghetti. So there's no losses.
Are lossy modes the same as leaky modes or I mix some notion?
Sorry?
Is the lossy modes the same as leaky modes?
Yeah. Same name. Yeah, some in some article they call it leaky modes. So they are resonances that you can probe from outside. Okay. So since I already spoiled you that during this talk, I will focus on the very simple case. It's for the grating. So if, and also we are dealing with sub-wavelength lattices, that means the period is smaller than the wavelength and the thickness is smaller than the wavelength. That means each rod here cannot contain one wavelength. So we cannot use the tight binding to describe, for example, these lattices because the element is too small. But on top of this, even that we are sub-wavelength, it's still big enough, so we don't use pure effective theory. So we are not in the metamaterial regimes. We still have band gaps for this. So how we describe this system? So if I write the dielectric function, now there is no dependence on y, so it's for x and z. So this is a periodic function that we can decompose in Fourier series. So as you can see in this Fourier series, we have this is a plane wave with different Fourier components, and the z is correspond to the vertical confinement. In our approach, we yes, it's idea. We will approximate this rating as a planar waveguide given by the zero order of the Fourier. So this planar waveguide also know very well how to solve the Gaussian equation to obtain guided mode, so propagating forward and backward, and then put on top periodic perturbations by this part, and this perturbation will create coupling between guided modes, backward and forward, and also to open band gaps, and also to fold them above the light cone to interact with the radiated continuum to create losses. So we have the coupling between guided modes and also make them leak to the radiated continuum.
I have a question. So if so we have the conditions A and H are less than lambda,
yes.
Does it mean that by addressing energy we can excite, for instance, only S modes or only P modes in this periodic crystal?
Yes. So for example, today we are mostly focused on TE mode or S mode. So we're not dealing with multi-mode waveguide. It's mostly at most B mode waveguide.
And if lambda is small, so it means that at the same time we will excite all bunch of modes of each single waveguide.
So each rods is not a single waveguide because it's very small. So each rods, as I mentioned before, cannot contain the light.
But if lambda is small.
Yes. If lambda is small, yes. But it's another regime. So people work also on lattices of couple waveguide and describe it by tight binding. So each waveguide is an element. So this is another regime that we need.
So small lambdas correspond to tight binding?
So if I have lambda smaller than this size, then each rods here can contain light. So that means that we can say that this is one waveguide, this is another waveguide, the third waveguide, and when they are close to each other, they can leak. So we can describe this system as a tight binding.
Yeah, and it's a two-dimensional Helmholtz equation in that regime.
So
there are many repeated experiments, and there are experiments by the Hoop and Nice. The group where they did such experiments with two-dimensional Helmholtz equation, then they can be described by tight binding.
Yeah. So in general, they will use this y-axis as Tamm because they write it as a paraaxial equation. So then you can mimic light propagation in Tamm by doing this. And yes, this is another regime. A lot of groups are working on it. But here we are in the sub-wavelength scale. vision.
But what's the direction of propagation of light in your picture?
So in here, the propagation of light is X direction.
X, Y,
Yeah, yeah.
not Y.
Yeah. So Y is inverted
You
translated.
basically have a plane wave in
Yeah,
one direction,
exactly.
which is
Yes, this is like trivial.
ky is equal 0 essentially.
At the end of my talk, KY will be different than 0. But but for by now, it's yes. You have like trivial propagation along Y and some like band structure along X. Okay, so now let's deal with the first part when we only care about the shape of the band structure or the real part of the dispersion. So as I mentioned before, we will start with the planar waveguide. So then in planar waveguide, we solve the Maxwell equation. We obtain forward and backward modes situated below the light cone. Of course, you can have other modes, which is higher order. So, but here we choose the thickness is small enough. So this is like single mode planar waveguide. So there is only like these red modes. And then if we put the perturbation by band folding, this forward can be shifted like one Dirac zone, backward we shift like one Dirac zone, and we have crossing. And at the crossing point, we will have interaction between backward and forward to opening some band gaps. So in this first part of the talk, we will focus on the first band gap, which is situated below the light cone. So there is no losses. So the interaction between these two is because the forward has been shifted one Dirac zone. That means that the interaction U is given by the first order of the Fourier series that I showed you previously. So then in the case here, this crossing, they are almost linear, so we can write it in very simple way. We have linear dispersion, forward, backward, and then the coupling. And this is a Hermitian Hamiltonian because we don't have any losses. And of course, you can diagonalize this very easily to obtain the band gap given by 2U, effective mass given by both U and the velocity. And here we solve with ab initio using some solar Maxwell equation, and we obtain a very good correspondence. So we can explain very well this first band gap.
In this Hamiltonian, is Kx referenced from P over A?
Kx is developing around this point.
Small.
Yes, small kx. Yeah, so sorry, this is not the same case. Let's go with like Qx. Omega naught is here. So this is band gap opening, but it's not engineering. How we can change the shape of this like boring parabola? So one of the easiest way that we thought a few years ago, that okay, we need to make them interacting with other modes in order to change the shape. So then we should work with some kind of thicker grating. So instead of having just one band gap for the fundamental guided mode, so it's an even parity, we have also the second band gap for the odd parity. But then they will cross each other. Since odd and even cannot be coupled, we need to break this vertical symmetry to make this blue and red couple. So one of the easiest way is to perform what we call the spatial etching. When we do the fabrication, then we do lithography, and then etch. Instead of etching completely, we will etch almost completely or half of the structure. So instead of having the grating like this, symmetry grating, we end up with what we call comb grating, the comb structure. And then the blue and the red are not totally odd and even anymore, so they couple to open like the mini gap. That is a hybridization between the odd and even. So you have C and B here. This is a perfect mix between odd and even. So this is a small recipe, but how we can describe this with some Hamiltonian. So this is a comb structure. We will decompose this comb structure into a symmetry grating on top of the planar waveguide. So in the symmetry grating, we have the backward, forward, that is coupled by the diffraction U. For the planar waveguide, there we have also forward and backward, but there is no coupling between these two. There's no intra-layer coupling planar waveguide, but you have interlayer coupling between the forward of the grating and the forward of the planar waveguide, the backward of the grating and the backward of the planar waveguide. So these couplings makes it happen by evanescence coupling. So light propagating here can also travel below and vice versa. So the whole Hamiltonian is Hermitian Hamiltonians, which is described in a very simple equation. As you can see, omega 2 and omega 1 is not the same because we don't have the same thickness and effective index. And also V1 and V2 are not the same because they don't have the same group index. So this is a very simple Hamiltonian, but I didn't show you, it's very powerful.
Sorry.
Yeah.
Is it correct? Positional view.
No, sorry.
And also, I have also a question. Do we forget about third-time splitting for now? Can it change somehow this picture?
About by implementing what? Sorry.
Third-time splitting.
TTM.
TTM, yes.
So here the TM is very high energy, and also they, in terms of we are working with ky equal to 0, so T and TM are not coupled because it's correspond to the symmetry y become minus y. So here we have the perfect separation between T and TM. So,
okay. And finally, how are in this picture directed the Poynting vector and the polarization vector?
So here the TE polarization is electric field is like this, and
this is electric field.
Yeah, and the TM polarization, the magnetic field is like this. So you have like EY for TE and HY for TM, and actually we have this C2 symmetry from minus Y to plus Y with this line. This one is the symmetric plane that separate T and TM. So as soon as we don't have KY component, these two family are uncoupled. So we can treat separately TN and TM. But this is a very good question because we actually also use the T and TM for entering some modes at the very end. Yeah. Okay, so this is the sample that we fabricated. So of course, when we fabricate real sample, we need to use real materials, use the silicon with very high reflective index. On top of a substrate, low reflective index, this is silica. And instead of changing the etching depth to control the symmetry breaking, we etch spatially like half of the sample and then changing the filling fraction FF to change the coupling U omega 1 and V1 from the symmetry grading. And by solving this 4x4 Hamiltonian, as you can see here, I only consider two lowest energy because by 4x4 we have 4 bands. So by changing this filling fraction, we can continuously tune the dispersion from accidental degeneracy, giving rise to Dirac cones, open the small band gap into parabola. The parabola the gap become bigger. So we have like heavier masses, and then this become the upper bands become a local flat band, or you have like infinite effective mass at kx equal to 0. So you have here the red dots are the electrical model that I showed you before, and below are numerical simulation of the reflectivity spectrum as a function of kx. And on top are experimental measurements. As you can see, we have a very good agreement between experimental and simulation and also analytical models. And this is very fun because here we have two extreme cases. We tune something from Dirac cones to flat bands. So from a very simple structure. So at that time, we are not aware, for example, with this magic angle physics, or people can change from direct cones into flat bands from the bibliography. But here we have some kind of similar. But of course, our flat band here are not a total flat band. It's only at the small region of the Brillouin zone. So I don't show you a Brillouin zone here, but it's about like 20%, 15 to 20% of the Brillouin zones. It's different from the flat band in the magic angles, or flat band in Cahomet lattice, or and the real flat band have is across the whole Brillouin zones.
Oh, sorry, is this k equal to 0? Is this in vicinity of the board? This is absolute variable, absolute k, or this is with respect to...
It's always in respect to the edge of the Brillouin zone. So with respect to the X point of the grating.
Okay, so, and you say that this guy on the left is Dirac cone, but in fact, this is just absence of anti-crossing, yes? Absence of anti-crossing, or...
So here, they actually this is not some kind of changing from weak coupling to strong coupling, because we have it at the very specific filling fraction. So that means that before, if I reduce the filling fraction, then I will open the gap again. So it's some kind of accidental degeneracy. When you have two modes of different representation, then when you make them degeneracy, you can open. You can make the direct cones, because as soon as I introduce some kx, then it breaks the symmetry. But at kx equal to 0, these two modes are opposite symmetry, in plane symmetry. Yes. So, but I won't go into details. But by group theory we can also have other ways to build these direct cones. This accidental degeneracy is so well known in photonics. That is different than, for example, in honeycomb lattice, or at k and k prime, you always have direct cones, whatever the parameters. But here is accidental, so you need to have the good parameter set to make them. Same thing for the flat band here. It's also accidental flat band. It's not some kind of robust flat band. As soon as I change the parameter of the system, the mass will change.
So another question. Initially in the Hamiltonian, you were having a vector of 4, but here I see only 2.
Yes. So
where are the
testing? You have also here, for example, this is the third band, and the fourth band is at higher energy. But then also, when you're at higher energy, you have chance also to interact with higher order guided mode. So that means that in general, we can only reproduce well in the analytic model the first 3 bands, because the basis is not 4. You can increase, because the number of guided modes, when you increase in energy and you reduce the wavelength, it's a lot. So it's, for example, if I want to reproduce well the 4th band, I need to make the 6x6 Hamiltonians, take into account also the higher modes. Yeah.
Can I ask the approximate value of the filling fraction for the rightmost panel?
Yes. So I mean the range of the variation.
No, filling fraction value approximately.
Yeah. So here is 0.58, remember, and there is 0.72.
So almost the gap is.
Yeah, the gap is small. Yes. So we have like 0.6 and 0.7.
So almost flat, almost continuous.
Yeah, it is continuous. So we have like we change a little bit. So it's actually in the publication we change every 0.02, and then we measure, and then sometimes we target some value we don't have the same, so we need to measure by AFM and SCM measurements. That's why we end up with some strange value. It's like 0.75, 72, and 0.58. But actually we target 0.6 and 0.7.
What is actual lattice constant in microns, nanometers?
So the barrier is 300 nanometer. 300 nanometer. Because we target the wavelength is in telecom range. It's 1.5 micron, where the silicon is transparent and high reflective index. And the thickness is about 400, 500 nanometer. Because if you want to have the single mode, is 200 nanometer, but here we have B mode, so we need to double. So roughly speaking, so I don't have the exact value in mind. Okay, so I show you that we can have nice shape by just single layer for the crystal. But can we obtain something more interesting with more than one layer? Let's go to multi-layer for the crystals. So this is our picture of multi-layer for the crystal. We have a lot, one on top of the other ones. So they are all sub-wavelength period. So we cannot use Tamm to modify them, to describe them. And also the distance between them are very small. So sub-wavelength interlayer distance. So we can have the evanescence coupling between them like the one that I showed you before. Now the main difference that if before we only have the grating on top of the waveguide, now we have grating on top of grating. That means you have intra-layer interaction for every modes. And in this talk, I will only focus on the case of bilayer crystals. So we have two of them. And also, I consider a specific case where we have moiré structure when the two pairs are not the same. So actually, this is a topic that I presented here 2 years ago in details. So today I will make a very light version to short recap, but I will show you new elements because before we only have theoretical measurements, but now very recently we now also have experimental demonstration of these magic distance flatbands. So the two grating have slightly different period, A1 and A2, but we don't want to be in the incommensurate regime. So the ratio, the two period is a rational number. And also we chose that n+1 period of the upper grating is the same length of n of the lower grating. So we can really define a moiré supercell lambda. And so I give also here the design. So the average period A0 is average of A1 and A2 is 300 nanometer. The thickness of each grating is about 200 millimeters. So we are in the single mode operation. So each grating will host only one family of guided modes. So how we describe the interaction? So we still have the intra-layer coupling by diffraction coupling U, top layer, bottom layer, and then the co-propagating modes of each layer can couple through evanescence V. The intra-layer coupling strength U will be dictated by the Philly fraction FF, and the interlayer coupling V will be dictated, governed by the interlayer distance L. So this is the two main period of the system, together with the third one that is the same for each moiré is the value of n. So each time you change n, you have a new moiré patterns. But throughout, for example, one parameter set, we will keep n constant and we will vary, for instance, the distance L or the fraction FF. At that time, we are motivated, of course, by the magic angle in twist-billiard graphene. So in twist-billiard graphene, the parameter is angle. So what is the parameter is closest to the angle here? To control the interlayer coupling, it's the distance L. So let's keep everything the same and just scan in L. Okay, so sorry. First, just describe the Hamiltonian. So this very similar to the one I showed you before of the cone structure. The only thing now is that we need to work with the real space if you want to describe it 4x4 Hamiltonian. So the kx now is replaced by minus I derivative of x here. And then since the upper layer and the lower layer are mismatched in terms of period, the local shift between the two grating is continuously changed in the regime of n is bigger than 1. So at some point, we have them perfectly aligned. So the shift is 0. So it's similar to AA configuration in the graphene. And here in the middle, for example, you see that they are mismatch shifted by half of the period. So it's AB configuration. So if we take a look of the diffraction U here, then there will be a phase shift between them, changing depend if we are at the beginning or in the middle of the moiré cell. So that's why you can see there's this phase term in the intra-layer of the bottom grating part.
In fact, it seems for me very strange how why we are working in 4x4 Hamiltonian, but not in Hamiltonian of size seems 2n plus 1. In fact,
so here, since we are starting at the beginning of the uncoupled mode, when they are not coupled, only that they are super far to each other, and also let's take the configuration that you don't have the rating, but it's a waveguide. So all you have like forward and backward. So that's why we start with 4 modes, and then we make them couple. But here but you are right, you are in the real space. If we go into Fourier space, then you need to take into account a lot of folding. And then the Hamiltonian in Fourier space is huge. You need to cut off at some point to see how many orders.
In K space is huge.
It's huge. In real space here, because it's hidden in this 4x4 in real space, that if you want to do it in K space of the moiré Dirac zone, then you start with, because it's very big Dirac zone, that you fold it into small Dirac zone. So the big Dirac zone is with the period A1 and A2. And then you have the small Dirac zone is the one, the moiré zone is with period big lambda here.
I think that the fundamental of the question is the following. We ask question why you don't consider the new unit cell, and the reason that we do not consider the new unit cell because we do not do type binding.
Yes. So this Hamiltonian is in some sense zoom out, very big zoom out from the system.
Yeah.
So we don't have the type binding from the beginning. I agree with you that if we begin from type binding, then the way that you are probably correct.
I think one element here will see all of
the
ice. Okay, so sorry, I misunderstood the So we keep n constant, Flynn fraction constant. The only thing we do is to changing the distance.
So can you explain? Maybe I lost that part.
Yeah.
The previous slide. So U is coupling back and forward.
Yeah.
Left and right.
Yeah.
Why? I thought before you explained that they are not coupled directly, and only when you add additional. So why are they coupled through the grading?
So because when they are far apart, you already have the corrugation.
Yes.
So they are coupling through the corrugation. So it's this is exactly the same feature at the beginning here. So this is this U. So you only need the corrugation to make them couple. Okay. And since the two gratings are super similar, so you have the same U. So that's and the only thing you take into consideration that when you put them close to each other, then you start coupling with V, and then you need to see one in the referential frame of the other. So that's why you have this phase shift. But of course, when V is equal to 0, this doesn't play any role.
Sorry.
Yeah.
A similar question that you take into account this phase factor due to the different publicity, but then can you comment on why the V the factor doesn't have anything position dependence of any stage.
So actually, there are two ways to put this phase. Either you put in U, or you make them absorb in V. So depending on the origin of the spatial, let's say we have X and X prime. So if you all have the same origin, X is the same as X prime, then the phase will be in U. But if X is shifted with X prime, then the phase will be absorbed in V. But at the end, it's just a unitary in the transformation. So we can choose either absorbing the phase in the interlayer coupling or in the intra-layer coupling.
Now we are chipping.
Why do not we put the phase to the diagonal of right lower square?
You can put them here.
Yes, for instance, why do not we add the phase to omega and to the omegas in the red square?
I mean, why we don't have it here?
Here also the phases, yes.
Because here is uncoupled frequency. So you don't. So the phase is when you have backward and forward see each other. So then you think of the upper layer is like this and the lower layer is like this. So that's why you have the phase different, and it's in the coupling. You don't have the phase in the. And also it's because it's a Hermitian, because if you have put the phase here, then it becomes non-Hermitian. Oh, but this is not a good answer, but then is it to show that we have the correct form of the Hamiltonian, that you should put the phase in the coupling term.
Shouldn't U be different for both layers?
In reality, they are slightly different.
Because you do have.
Yeah. So when we do the real new analytical model, we extract the parameters, we put them different. But here is for the sake of simplicity, I put them the same. So omega are not exactly the same, and V are not exactly the same. But in the limit also N is very big, they are really, really close. So we perform first the real ab initio simulation by solving the Maxwell equation. So this is very nice because you know that in solid state physics, ab initio calculation is huge because we need to take into account all of the number of the items, and also we need also to take into account also the relaxation of the graphene, but by strain. But in our case, since the wavelength is much bigger than the atomic scale, so there is no strain effect, even when we put one grating very close to the other one. So we don't be afraid. We are not afraid of like deformation of the grating. And also it's 1D grating, so the calculation is very fast. So that's why we can really solve the band structure of the system. And as you can see here, when they are far apart, actually it's not very far, when the distance is almost at the period, there is no interaction. So we only have this band folding with the shared band gap between the two layers. But as soon as we make them closer and closer, for example 0.3 here, we start observing the emerging of the mini bands of the superlattice inside the band gaps. So by the analogy with solid state physics, I call this guy electron light moiré band, and it's whole light moiré bands with respect to these fake Fermi levels. And you can see that this superlattice band is pushed more and more inside the band gap when we make them closer and closer, so the limit is where L equal to 0. And most interestingly, as soon as we have some very specific value of the distance, we can make the moiré bands flat. So these are numerical simulation, and you can compare it to our calculation using the Hamiltonian I showed you previously. So the only thing that changed, you can see that if in the calculation here, the electrons and holes moiré bands are flat simultaneously, in the real simulation, you don't have them flat simultaneously. You have first, for example, here is a whole line moiré band is flat. If I change a little bit the distance, then this guy will become flat. So here also, here I only focus on the whole line moiré band. If I want to have the electron line moiré band flat, I need to change a little bit the distance. It's because we have some approximation. So in our models, as I mentioned before, like the omega naught is not the same, or U are not the same, and other behaviors. For example, when they are super close, then the presence of one will change also the effectiveness of the other one. So omega naught should depend slightly on L, for example, but it's not taken into account here. But the important message here is that
I think that the key of this is that you lose the particle symmetry by two layers are different. Two layers are the same.
I change, for example, number of n, so we don't have the same moiré, and we tune the distance. And as you can see, we have by different n, we have different number of magic distance. We call it magic distance here because it's at this distance, the bandwidth vanish. So for this theoretical works, we change the interlayer coupling and fixing intralayer coupling. But for experimental demonstration, it will be difficult to have the fine control of the distance. So what we chose in the experimental demonstration is to have a very short distance. So L is small, it's less than 100 nanometer. And then we finely tune the filling fraction to change the intralayer coupling, the U-turn. And for the fabrication also, the two layers now are not the same anymore. One is made from amorphous silicon. The lower one is made from crystal silicon, so they don't have exactly the same reflective index. So this is the view of the fabricated sample on top. So you can see the variation here is from microscopic image. So the scale is big compared to 300 nanometer of the period. So what we see here is a moiré modulation. So it's not the period of each layer. But then we do on purpose to have a small region. Actually, it's not small, it's few microns. So it's more than enough to perform measurements. But we can measure the band structure of the upper layer, the band structure of the lower layer, and also the one of the moiré supercell. So you can see here, we have the band structure of the upper layer, the lower layer, and now they don't have any shade band gap anymore, like in the theory. But nevertheless, even that they don't have the shade band gap, as soon as we put one on top of the other one, we observe these moiré bands emerging. And why I know that it's moiré band? Because if you zoom in it, the periodicity is really given by the moiré period. And now we focus on the moiré band and we change the filling fraction. So you can see here by changing filling fraction, we can reduce the bandwidth. So up to 2 MeV. So 2 MeV is really, really small compared to this scale. So you see we have almost flat. So we are observing like the magic configuration of almost magic configuration. Maybe it's somewhere here, but then we need to fine tune it more.
And
the filling fraction.
What's the experiment?
So the experiment is reflectivity measurements.
And what is the geometry of this experiment?
Sorry?
Geometry, falling angles, falling angle detection.
Yeah. So this is what. So we perform in what we call is Fourier imaging. So that means that we take the picture of the sample, but not in real space, but in Fourier space. So then you have Kx and Ky, and then we put the picture through a spectrometer. So we sacrifice Ky to energy, for example. So that's why you have energy and then wave vector. But this is more complicated because a lot of scattering. So if we present the raw reflectivity, you have a lot of noise. So what we present here is not the reflectivity, it's actually the derivative of the reflectivity. So that's why when we have the resonances, is when your derivative is 0. Because if you have the Lorentz, you have some big like this, so so that's why we fit in the middle. So it's technical part, but maybe
but what are the directions of lasers and
so we make incident light and we collect light. Is all happens at the same time under a microscope objective. So we inject from every angle and we collect from every angle, but then we have a sensor that can separate each pixel into angle. So this is the same thing like when you take a picture of your cell phone, you have X and Y position, but you can do the Fourier transform by putting lenses, and then you have Kx and Ky. But you need energy, so we need to put it through our spectrometer. But in the spectrometer, you lose 1 degree of freedom. Here is Ky. You don't care in Ky. So that's why we have energy and Kx.
Yeah, but still, so okay, so you have two arrays of waveguides, and you irradiate from all directions.
I irradiate on all direction, and I collect from all direction, because there's a microscope objective on top that can excite in some cone. So we have almost all direction. It's below we call numerical aperture.
And then we put Fourier lens that corresponds between angle and position.
Yes. So basically,
Use your with your hand.
no, I remember this. I can draw.
You can use your finger.
Okay. So you come with you excite with every angle. So this is a sample, like relay of sample. And then when it emit, for example, it's given angle, it's correspond to this position. For another angle, it corresponds to other position. So if you put the spring here, so by this point is for this angle, and these points for this angle.
So basically they do Fourier for you.
Yeah, so I mean for Fourier transform of light very easy. It's lens. You put lens each time you put one lens is a Fourier transform. So here you have one lens with Fourier transform. In general, you want to have real space. You have two lenses. Then in two lenses you have 1 point here, and then correspond to 1 point here. So here you have real space, real space. Yes, real space, Fourier space. So it's each time you put lenses, you do Fourier transform. And this one is single shot measurements. It's like taking a picture. So the difficulty is not the measurement itself, but it's fabricating the sample to control very well the alignment and then the shifting. So it took us 2 years to master this fabrication. So,
I have a question. How was this data agree with our theory paper?
Complicated. Yeah, because here we don't have the same, you see, same written, the two are very different. But since our theoretical paper, there are other groups that they show that even the two rating are with different offset, you still have this flat band. And here we have behind or show here the numerical simulation that agree well with these results. But the article paper is some kind of simplify. How many times I still like? Okay. It's difficult to go for the non-Hermitian part. Maybe I will just some flavors and then you stop me. Yeah. Okay. So now we change the shape of the bands, but before now we focus on the line width because we have losses. So before we are focused in this band gap. Now we jump into the middle of the light cone. So we are exposed to the losses. That means the Hamiltonian I showed you before, simply with just coupling U doesn't work anymore. We need to use a non-Hermitian Hamiltonian. And this non-Hermitian Hamiltonian will employ what I will show you just after, that people call Friedrich-Wingen interference via loss channels, because each guided mode, when folded into the light cone, will be leaky modes that will couple to this radiative continuum. So the seminal paper in 85 from Bingen successfully described the interference mechanism of two resonators, both radiating to the same radiative channel, gamma 1 and gamma 2. They can also couple in U, and they use this very simple scheme to explain the formation of so-called bow state in the continuum that was predicted by von Neumann and Wigner in the 30s. So how the Philip-Bingen Hamiltonians look like? So the coupling, the Hermitian part is the same that we saw before, omega 1, omega 2, and U. The interesting part is the non-Hermitian part. So you have the losses of H resonators, gamma 1 and gamma 2, standard. But the fact that they radiated and coupled to the same radiative channels, I mean, they can also exchange losses. So this is interference. This is very different from the photons. For photons, you have it become thermal, so it's not easy to do interference. But here for photons, they can exchange losses. So you can write the loss exchange mechanism, like the square root of H losses, and also you have this phase shift. So we can understand this phase shift is when you need to have this one and this one radiate at the same time in order to be able to interfere in phase. So
basically, what does it mean that we emit from first guy, then in some radiative channel we have some loss of phase, and then we go to the second resonator.
So this like.
So U is kind of coherent.
Yeah, U is like some kind of near field coupling. So without any, you don't interfere through the losses. But you can think of this one radiated to the continuum.
Yes.
With some.
Does it lose the phase here in the radiative channel?
So here, when you radiate it, you have a phase because you become plane wave. So you think that you put emitters that is like vibrating inside the structure, that then it's coupled to outside in terms of plane wave. So if you have another modes, then this plane wave also can go to the modes, reabsorb. So you can think of this two-way mechanism. But this more like some kind of interference. So it's the demonstration of this, you can, in the quantum mechanics point of view, is explained in this paper. And there's another, and this ultimate quantum version is a subradiant and superradiant. You can think of two-level system that is currently coupled. And then one will be superradiant, like oscillating, like spontaneous emission become very fast, and the one is subradiant. And so this will very similar to this scheme. But this scheme is work also for classical waves, like the one that we are discussing. So if I use the same Hamiltonian that I showed you before, and we perform this very special condition that we change the detuning of the losses and the detuning of the frequency to satisfy this condition. And also we need to have them in phase, so sinus equal to 0. In this case, we have one eigenmode become superradiance. So take all of the losses, gamma 2, and the other eigenmodes is like subradiance. Here is lossless, and this is called bow state in the continuum, because even these modes situate above the light cone, but it cannot radiate to the continuum due to this distractive interference. And in general, this condition can be satisfied very easily if we choose gamma 1 is very close to gamma 2. In this case, this will be satisfied when omega 1 is almost equal to omega 2. So if we take a look in the band structure, when omega 1 is equal to omega 2 is when we have the anti-crossing. So when you have leaky resonances and creating anti-crossing, in general, it is very easy to have one of them lossless and the other one become very lossy. So this branch is a dark band mode, and this band is a bright mode. So this is a scheme that helps us to engineer barometric in the continuum, because we just need to make anti-crossing in the momentum space. And in general, not all the times, because also in this condition, we can engineer some lossless state. Okay, so how we bring this general scheme into our example here. So it's super easy for us because omega 1 and omega 2 is this forward and backward modes. And then gamma 1 and gamma 2, since they are the same modes, so they should be the same. So gamma 1 equal to gamma 2 equal to gamma. The phase, one is forward and is backward, so the phase is equal to pi. So these, the Friedingen Hamiltonians will be written under this form. Okay, so this is 2 by 2. We can solve the eigenvalue at kx equal to 0 very easily. So when kx equal to 0, we have the same losses and the same frequency. The detuning of losses, detuning of frequency is equal. So we should expect bouncing the continuum is the case. One of the modes will be purely real eigenvalue. So this is lossless, and the other modes we take all the losses. So 2 gamma. So how do we draw it? So when U is negative, so omega plus is the lower band. So the BIC is situated kx equal to 0 here. The other one is the lossy branch, this guy. If U is positive, then we have band flip. So the dark branch now will be the upper band with the BIC here, and the bright branch, lower one. So this reminds us of the band inversion in turn insulator. For example, if you can change the topological phase by closing the gap and reopen again, so we emerge with 2 different topological phase. Of course, I don't forget about any topological phase here, but if I want to cross from this to this, I need to close the gap. And then we close the gap, we put U equal to 0. Since we are dealing with non-Hermitian, so we don't have direct points, but 2 exceptional points. So as you might know, exceptional points are when you have the simultaneous degeneracy of the real imaginary part, and also we have eigenstates, coalesce, and they are singularity of non-Hermitian physics. So a lot of interesting things happens at exceptional points.
And what is the measure of the length of this bar? Just gamma over V?
Yeah, exactly. Gamma over V or 2 gamma over V. So I don't remember exactly. So can we observe it experimentally? Fabricate out of sample. I don't mention much in detail why we need to have this black mirror here, but basically again we want to change U intra-layer coupling by again changing the filling fraction. So we follow what k equal to 0, the dark branch and the bright branch. You see that the bright is almost constant, the dark branch cross, and so we might have EP here, exception point here, and have from this to this band inversion. So here are experimental measurements on the left part and numerical simulation on the right part, together with analytical calculation. So the model we use is slightly more complicated. We have higher order, so that we don't have this flat here, but there will be some kind of also lifting of the degeneracy of the real part between the 2 EP. But you might see very well the band inversion. This is a dark. Why we know that it's a dark? Because from reflective measurements, we don't see the resonance anymore. That means the modes here are lossless because we try to probe the modes from above. So if there is BIC, so bouncing in the continuum, so you cannot probe it from outside because it's uncoupled from the continuum. So it becomes the resonance vanish locally. So we know that is a dark branch. And so you can see the dark switch side, but let's focus first on the EP case, U equal to 0. So in the EP case, so again, experimental simulation left and right, and I brought on top the model. So it's slightly more complicated than before, because you see that outside the EP, the imaginary parts are not degenerated, and inside the 2EP, the real part is slightly lifted. But we really observe the formation of exceptional points. And so I think this will be almost the last part, because I run out of time. But we try to demonstrate something interesting with these exceptional points. But as exceptional points, there are a lot of weird things happens. For example, if you encircle exceptional points, then you will swap eigenstate from one to the other one. Other phenomenon is that it's like you miss one dimension, because in general you need to have two vector to map all the Hilbert space, two-dimensional. But here, when you have two eigenstate coalesce, then it's like you miss one eigenstate to map your Hilbert space with a lot of strange things. But we focus on one of the properties that didn't observe yet in the experiment at that time, that people want to see what is the density of state of light at the exceptional points, because the density of state dictate how light matter will interact by the Fermi level rule, or Fermi golden rule. So if you have more density of state of photons, then light matter interaction will be stronger, so you can enhance the spontaneous emission. And these theoretical papers predict that if you have two exceptional points, two resonances that are not degenerated, so each of them has some density of state. If you make them degenerated, the total density of state at the degeneracy is not the sum when they are not degenerated. It's bigger. So mathematically point of view, at the exceptional points, the density of state is given by a square Lorentz. And when they are not degenerated, they are two Lorentz. So the square Lorentz will be 4 times bigger than each Lorentz. So you will have 1 plus 1 here is bigger than 2, which should be expected it's equal to 4 in terms of density of state. So this is why we try to demonstrate it experimentally. So in this work, we need to have some emitters to probe the density of state. So we put very thin layer of quantum emitters, here's quantum perovskite on top, and then we perform the photoluminescence measurements from which we can extract the density of state. This is from the experiment, and this is from theory. From this, you can see when you are not at the degeneracy, you are far from the degeneracy, you can take these two signals, is for example, the green and the red, have like 1, and at the exceptional points, we go to 2.56. So here is bigger than 2, so we are, and the error bar is big enough to be sure that we really have the enhancements at the exceptional points. So at that time, we are happy, but the enhancement factor here is smaller than what the theoretical limit predicted, go to 4, and you might ask me that we don't see the splitting that I showed you before. We see some kind of very bright dots. So where are my 2 exceptional points? So actually, we price a big price. We pay a big price to put emitter here that the matter itself have non-relative losses. So we add non-relative losses to the system. So if there is no non-relative losses, then you can see very well the 2 exceptional points. But as soon as you put non-relative losses, then you have it's broadened and become the bright dot. And the end of enhancement, when you have non-relative losses, so it drops. So 2 is a limit of Hermitian limit. So we are in our result, we are considered at this point. And the limit is 4. So in this case, it's enough for us to show that we have endless enhancement at the EP. But so this will be, I think, the last piece of results I showed from very recent work. We engineer new sample using very good emitter. So 3.5 quantum well, so without any non-negative losses. And we engineer now the exceptional points by other mechanism that I don't have time to explain here, but this point out one of the question you asked me before is raising from the TE and TM coupling. So if I have KY equal to 0, there's no TE-TM coupling. But as soon as I have some non-zero KY, I can make the T and TM coupling happen. So for example, I can start, so for KY equal to 0, I have one TE mode, one TM mode. So this is KX, omega. So they cross because they KY equal to 0, and this one is K0. But if I work at Kx equal to K0, and I start introduce KY, then T and Tm will couple. And if I chose T and Tm modes that have different losses, so this I can basically write the Hamiltonians H, T, Tm will be like omega naught plus ky VTE omega naught plus, so not the good way because it will be KB.
You can press plus there on the right, lower right.
Or you also
I can.
Okay.
Okay, good. So no, so the coupling is a KP, so it should be like KY alpha, alpha KY, and they have different losses, gamma TE, I, gamma TM. So it's something like this. If we solve this Hamiltonian, we end up with this kind of exceptional points. And you can see now very clearly in the photoresistance measurements, the enhancement of the photoresistance, so the endos at the exceptional points. And if I take the red, is at the exceptional points, you have the factor 4. When you are out of degeneracy, so the blue is 1. And when you have the weak coupling regime or Hermitian degeneracy, the green, yeah, the 2. So we really show the theoretical limit of the enhancement of the endos at the exceptional points. Okay, so I think I will skip this. So it's further some topology related to the band inversion of the Tamm. So let's go to the conclusion. So I think maybe Zoom someday can tell you this result because it's from our recent work together. So as conclusion, I hope that throughout my talk, I convince you that photonic band structure in single and layer fluid crystal can be engineered on demand via mode coupling. So we can, for example, engineer accidental Dirac points, local flatband by just changing coupling in a very simple design, and by putting together 2 layers one on top of the other one, while a scheme, we can also mimic the physics of twisted graphene. In this case, we have almost perfect flatband across the whole brane zone at a specific parameter set. In this case, I show you here is magic distance, but we also have magic free fraction, magic, I don't know. So this for us will be like some kind of accidental configuration that make the flatband. And if we work above the light cone, then we have more than just the shape of the band structure, but also the line of the losses that is dictated by Wien interference. So we can engineer bound state in the continuum and make band inversion. And at the transition of band inversion, we have exceptional points. And photonic platform is very powerful to study this kind of physics because losses is natural for light. And every time we take pictures of light doing spectroscopy measurements, we are dealing with non-Hermitian physics. And we can really see the loss or see the lossless because the dark branch is lossless and we see it because it's not there. So it's like black hole. When people show you a picture of black hole, actually we never see the black hole. We see light outside the black hole. So it's the same thing for bound state in the continuum. So for the perspective, so because we want to explore more about the unconventional localization at magic flatbands. For example, we have recent work to show that how many supercells we need to have the confinements. We have this to have the 3 supercells. What happens when we go in the incommensurable structure? This is not ordinary Abri physics, but maybe we can also expect some mobility edge with this quasi-periodic structure. And what happens if we implement many-body physics in this system? And for the bound state in the continuum, the lossless state that we didn't have more time to talk about today. So it becomes very interesting also in the strong coupling regime when we make photonic bound state in the continuum strong coupled with other material quasi-particles now in the serious accidents to have accident particles. Because then we can borrow the topology from bound state in the continuum that I don't have the time to mention, but with the nonlinearity, the many-body physics coming from accident particles, engineered for example bound state in the continuum with Bose-Einstein condensation. So it's some experimental work that with some collaborators we did recently. And for the theory, so we developed some kind of mean-field theory of Bose-Einstein condensation of accident particles at the PIC. And we wonder if there will be new regime of superlattice, and also what happens if we don't work with the bound state in the continuum, but with exceptional points. What should we expect? So for this, I want to thank you for your attention, and also thank you for all of my students and postdocs who work mostly on the experimental talk, and my various collaboration on the theory. Thank you.
Thanks for just a talk. A few good questions.
In the experiment for the Erdos enhancement, how can we confirm this enhancement comes from the exception, not from the gain or high Q kind of band between the exception points in the experiment?
So I think I turn off this because we have another work to not with exception points, but with the like flat bands or other carbon structure where we map the variation of the Erdos coming from the theory and the variation of Erdos coming from the experiment, and we can really see the one and one corresponding. Because here exception point is, let's say, it's some kind of boring because you only have one piece. But if you have like band gap, band edge, different curvature, so you calculate the Erdos from solid state physics density of state and the energy by integrating all the wave vector, for example, you have some variation. And this variation we can reproduce nicely by extracting from the photoluminescence. But of course, we need to work where in the regime where we have no gain. So here the emitters are only there for probing the Erdos. So there is no gain. We are far from the lasing regime. And also we need to have broadband emitters. So that means that we don't have like narrow emitter. The emitter are, let's say, everywhere, and they need to have also very high quantum yield. So that's few conditions. And then from the PL measurements, we need to do also some post treatment because the emitters has itself a spectrum. So we need to deconvolute the spectrum of the emission, the emitters, to extract what is really coming from the LDOS. Yeah, so this many like technical challenge, but I think in the supplemental methods of our PR paper here, we explain step by step how to extract the LDOS from the raw data.
So what is physically the radiative channel for your system of waveguide array?
So the radiative channels is this vacuum. That can host plane wave. So
you see a vacuum.
Vacuum. So here we have every light can exist here. So it's host plane wave. So
no additional resonator is needed.
Yeah, there's no resonators. So this other people can use a waveguide. So if you have like one resonator here, one resonator here, they can put waveguide, and then you have link like this, and then light can need some time to travel. But so we have like two resonators separate in space. In our case, all our resonators are the same position, so they are not separate in space, but they all radiate to the same continuum. So
how is defined the phase phi in this Hamiltonian?
So good question.
What is really just physical meaning of this phi? I still cannot capture, and I want to understand.
Yes. So in the case of, I show you I don't want to go through all this. In the case of just two modes, forward and backward, they are the same. They are just so the phi, you can show that it's like pi phase shift. There is another phase that can take into account. So I need to, I write it somewhere here, the full picture. I go forward, yeah. So you can see here some interference also coming from the fact that they don't have the same polarization. So in the case when there's no KY, then the TMOS is like this. But you introduce some KY and let's see some TMOS, then the forward and backward are not the same polarization anymore. So that means when they interfere, you need to take into account the fact that they are not in the same polarization, so the interference is not totally constructive. So there's this cosine term that is on top. But then also it's better. So if you have this archive, and we develop also ab initio, step by step, this Hamiltonian. So that's here is just some kind of hand waving. How we
maybe this is somehow stimulated radiation by first guy from the radiation of the second guy. Can it be interpreted like this?
No.
Maybe.
Yes.
Okay. I have some broad questions. It seems that you have dealt with many Hamiltonian things, which is very similar to the physics in the electron band structure. So I have some questions regarding the difference between the electrons and photons. So is there any merit realizing similar topology or something, many band structure things with the photonic structure? Is there any merit of photonic crystals on electronic periodic packaging?
So actually, our approach here is very similar to what we learned, like weakly electrons in the weakly perturbated potential. When you have like 2D electron gates, parabola, and then we fold it and we open the mini band gap. So it's a toy model, because in general, in real solid-state physics, it's very complicated. So that's why our platform here is similar to a real toy model, because we have some simple Hamiltonian that cannot exist in solid state physics. Apart from you have 2D electronic gates and you put some very weak perturbation on top. But when you take the real piece of solid crystal, the band structure is quite complicated. Yeah.
And second, both electrons are fermions and photons are bosons. Is there any difference arise from that difference?
In single particle picture, band theory is here the same.
Yeah, so you can have band structure the same, but the measure quantity.
Yeah, of course. Yeah, the merger. Yeah, I talk about the band structure. It's the same. But of course, the merger, for example, in electron, you need to be careful to have the Fermi level. You need to populate electrons. It's really difficult to inject electrons at the given energy and the given wave vector. You need to dope and do all of these things. But in photons, it's bosons. So if you want to come resonantly, you just need a good wavelength, good laser, and you change the angle. So you have a good infinite wave vector. So you can put photons resonantly easily. And also, I can really measure my band structure in the setup in room temperature, single shot measurements. If you want to do it with the real electrons, like in twist-beer graphene, you need to do arc-based measurements, and it's quite complicated. So it's, yeah, I think there are some same, but still very different.
So one thing I can comment, because the photonic is boson, the electron is fermion. For example, even you can have the boson bandwidth finite Chern number. You can never measure the exact whole conductivity to be quantized, but electron you can.
Sure.
We have one more question.
So I remember that you mentioned about difficulty of engineering gain loss kind of situation. So can you elaborate on that? How difficult is that to expect?
Yes, because actually to have gain and losses is not an issue, but to put them in sub-wavelength scale and distance precisely is difficult. So if people do it in time binding, then you put them, sometimes you have gain, sometimes you have loss, it's far apart from more than wavelength. But in our scheme here, if I want to have this is gain, this loss is gain, is loss, it's complicated. And even with the time binding, it's very few groups manage to do it. But you don't need gain and losses to do non-Hermitian physics. You can have losses and less losses. So you just need different losses. So then you can put them offset outside to have this pretty symmetry.
Okay, so still here at the end of this week. So we have further questions. Let's discuss with him, and thanks again. So, second.